Okay, so today, our major goal today is to be able to calculate areas. You said, well, isn't that what we've been doing, area under the curve? Well, actually, mute yourself, Nate. Yeah, area under the curve is a very specific type of problem. If I want this, yes, that's just the integral from a to b of f of x dx. But that means that I must be bound by a curve and the x-axis and two vertical lines at all time. You're never going to calculate that area. That's not even an interesting problem. What if I wanted to calculate an area, let's say, you know, just sort of out here? In other words, this doesn't look anything like this. So this is kind of the norm. We want to be able to calculate any area bounded by perhaps multiple curves. I might have 3 or 4 different curves, and where they're intersecting, I want to be able to calculate. So that's more of a general case there. So let's start with the simple one. Let's suppose, all right, I'm going to have 2 curves. And I want this area right here. Okay, I want the area bound by y equal f of x, y equal g of x, x equal a, x equal b. Okay, well, how do I find that? That seems like that might not be quite as easy. Well, let's do it the simplest way we know. And I love using this analogy every time. If I had a circle, and then I had a circle inside the circle, and I wanted you to find the area between the circles, how would you find that? I mean, would you, divide this up into sections and trying to do weird stuff, or is there a real obvious way? Anybody want?
Subtract the small circle from the big circle.
Yeah, that's the oh duh approach that sometimes we forget. Oh, okay, I want to find the area between these two. So why not take the area under the curve of f of x and subtract the area under the curve of g of x? It's like, oh yeah, but we don't always think of that. That's the obvious. That's the part I want you to say, oh duh. So clearly the area under the curve of f of x would be the integral from a to b f of x dx. Oops. The area under the curve of g of x would be a to b g of x dx. And we just said we want to subtract those areas. Now, we have a rule that when we are working with limits of integration where we end and then start and then we can combine them, these are the same limits. So that's not that one. But we also know that the integral of a scalar multiple, the scalar can go in and out. And we know that the integral of a sum is the sum of the integrals. So putting those concepts together, we can actually say this. Okay, because again, think of this as -1 times. So, okay, then I'm going to go plus -g, and then I'm going to add the integrals. So essentially, I can do this with one integral. And that wasn't necessarily obvious at first, but I want it to become obvious. Now I'm going to show you the most efficient way to get this result in general. And it is not to do this. This is kind of the longest way. So what we're going to do is we're going to go back to our picture and we're going to subdivide it like we did before. Now I want to just take an arbitrary rectangle. Let's say I take that one. And we're going to call that the ith rectangle, right? First, second, third, fourth, and so on. I want to describe that area right there. So the area of my ith rectangle, well, what's the area of any rectangle? Isn't it base times height? Well, my base is clearly the delta x, and my height would be the difference. So my height would be the difference of these things, and I'm going to write it like this: f of xi minus g of xi. Okay, that's the height of that rectangle times delta xi. That is the area of my ith rectangle. I'm going to erase this so I can figure it in. Now, I'm going to show you all the in between, and then I'm going to show you where we can skip steps and make this more efficient. We now know that I can give a reasonable estimation of the area by taking the limit of that. You guys have done this before, and you did this particularly well. And then my area, of course, was the limit of this as the norm of the partition headed to 0 of this. It's gonna be a little tight. Delta xi, okay. And then finally, I got to the definite integral of this. Okay. We know that this is the sequence that must occur to get to here. But actually, once you have this statement right there, I have a statement for what does this particular area look like, the ith one. If I can come up with a general way of describing every single rectangle, because if it were the first rectangle, we would have said f of x1 minus g of x1, delta x1, and so on. So if I can describe the ith cut, then I can go directly to a sum, then I can go directly to the limit, then I can go directly to the integral. Nope. We're going to do this every time. You see, I think you'd like that better. Once I can express that, I can go directly to the integral because the path in between is always going to be the same. It's always going to look like that until I get to the limit, and then I'm going to translate the limit into the integral. I'm telling you, no. Translate that directly into the integral. Tremendous time saver. You're going to do this all 3 semesters, this type of problem. Yes, there is a Riemann sum. Absolutely, there's a limit involved. But the most important thing for me is to state that integral. And that integral looks a heck of a lot like my arbitrary slice. And so that's kind of how this is going to work when we're finding areas. So let's do a very specific problem. All right, so I'm going to give you the language that you're going to see also. So we'll say, find the area of the region bounded by, how about y equals 16 minus x squared, y equal x equal -3, x equal +2. Okay. Now I gave you a lot of boundaries there. Now you never have to do the next thing, but you absolutely always have to do the next thing, and that is draw a picture. What I mean by you never have to, because no one's ever going to ask you what the picture is. You're never going to be able to set up an integral if you don't start with the picture, because you'll never know where your boundaries are and your limits of integration. So part of the reason we do all those graphing concepts is so that I can find areas and then later volumes and in later 3-dimensional stuff. So always sketch a picture. Now, does your picture have to be perfect? No, it just has to be representative. I have to have the correct curve on top and the correct curve on bottom, things like that. So I want to draw a fairly reasonable picture. So I've got y equal x. I've got this guy here. Excuse me. And it's going to look something like, I don't know, like that. I've got x equal -3. X equal -3 would be about here. And x equal 2 will be about here. How do I know that? Well, because that's 4 and -4. All right. So I got a lot of stuff going on here. Oh, this is why I needed to draw a picture. I have a downwards opening parabola. I have a line, and then I have 2 vertical lines here. So if you do a quick check here, it looks like my region is this thing right here. I think it's pretty clear. Maybe I'll outline it. It's pretty clear what my region is. Oops. Show you the right region. There's my region. Now, I would like to make an arbitrary slice. Now, the first thing is, as an absolute mathematical statement, I can always set up every problem that exists with vertical rectangles or horizontal rectangles. And we're going to do both today. Now, here's how you decide. How do I know if horizontal will be more efficient? Well, first of all, I'd like to only do one integral if I can. Right now, if I slice this from left to right with vertical rectangles, every single rectangle that I could possibly draw will have something in common. Every single rectangle will have the parabola on top and y equal x on the bottom. From left to right, that will never change. That's huge. That means my boundaries are always going to be the same. Now, I want you to think about that for a moment. If I did horizontal rectangles, up here, I'd be going from parabola to parabola. Here, I'd be going from parabola to line. Here, I'd be going from line to line. Here, I'd be going from line to diagonal line. I would have so many different sets of boundaries, and I'd have to have a different integral for each of those sets of boundaries. That would be really, really complicated. But the vertical rectangles, which is what we're going to go with most of the time, probably, is a fairly simple notion. So what is the ith slice? Well, let's remind ourselves, this curve was y equals 16 minus x squared. This curve was y equal x. And x clearly is ranging from -3 to 2. So with that said, the area of my ith slice will be this height, which would be top curve, and I'm going to write it like this: 16 minus the square of xi minus the bottom curve, which would be also xi, times delta xi, x ranging from -3 to 2. Now, the reason that's important, because ultimately those are going to be my limits of integration. Okay, they're not part of the integrand, those are my limits. Oh, okay, well, that seems easily enough. I don't have to do any algebra here. I'm not going to have to distribute a negative or multiply or do anything. I can now say, I can go directly to the integral. Area equals the integral from -3 to 2 of 16 minus x squared minus x dx. Now, that wasn't complicated, but having the picture certainly helped me determine what order of things. Now, the level of difficulty of this, very low level. The quiz you just turned in, every problem was significantly more complicated than this one. Okay, so when I'm integrating this, I'm going to have 16x minus a third x cubed minus a half x squared from -3 to 2. We would love to be able to use symmetry, but there's no symmetry going on here. Okay, so at 2, I'll have 32 minus 8/3 minus 2. And then at -2, I'm sorry, at -3, sorry, -48. And then here, positive 9. And then here, minus 9/2. Think I got that right? No, I'm just going to use my calculator, keep it easy. So 32 and my handy dandy calculator says the answer is 425/6. Okay, now there wasn't anything difficult when I got to here, but I want to get this right. This problem and most problems of this nature are all about, can I come up with the integral that represents the problem? In fact, in a lot of situations in both math and science, your goal is to come up with the integral and then wave at it as you're walking away. In other words, a lot of times that will be the answer to the question. Because if I can state the integral, then absolutely I can finish the problem. But if I can't state the integral, then it's impossible to finish the problem because I don't have anything to evaluate. So our emphasis now is not so much on the integration, like I said, as getting this. All right, let's try another one. Oh, another 10 maybe. We'll see. As many of these in as we can. Eraser's starting to fill up with ink. See if I got another one here. There we go. All right. Oops, sorry, not 4. What am I thinking? X plus 2. Now, it might seem like I didn't give you enough information there. Wait, but I didn't tell you X going from what to what. Well, maybe we should start by trying to draw this thing. All right, I've got y equal x squared. And I've got y equal x plus 2. Oh, okay. I didn't have to tell you X from what to what. I've enclosed a region, haven't I? Okay, so I said the area bounded by these two curves. That would be this area right here. Now, it might be a good idea for me to find those 2 points. Okay, because there's no guarantee that this is a simple matter. So I want to find those 2 points. So in order to do that, I need to figure out where these 2 curves intersect. So let's just simply solve x squared equals x plus 2. If I do that, we'll have x squared minus x minus 2 equals 0. So that's x minus 2, x plus 1 equals 0. So x is 2 or x is negative 1. Well, let's double check. If x is 2, then y is 2 plus 2, 4. Y is 2 squared, 4. Good, got that one right. If x is negative 1, then y is negative 1 plus 2 or positive 1. Y is the square of negative 1, which is positive 1. Good, so I got that one right. So that's negative 1 comma 1. So I want the area between these. Now, I could go horizontal, in which case I'd be going from line to parabola, but then down here, parabola to parabola. So vertical is probably easier. And we haven't done anything yet where we have to switch, but another governing factor to determine whether you want vertical or horizontal rectangles is how are your boundaries described? Are your boundaries given as y as a function of x, or are your boundaries given as x as a function of y? Okay, because that actually matters. If your boundaries are x as a function of y, then horizontal rectangles may be easier because I don't have to rewrite my functions. Okay, so right now when I'm setting this up, I don't need this anymore. The area of my ith slice, and by the way, I've been doing this for a long time, and I do this every time. I don't ever have a problem where I don't do this first. Now, this is the line. So maybe you want to write it down, I don't know. And this is the parabola, just so I don't get them mixed up. Right now, the upper is the line, the lower is the parabola. So I'm going to subtract xi plus 2 minus xi squared, delta xi. And again, now x is going to range from what to what? Leftmost x is negative 1, the rightmost x is 2. Now, it is very important because we identified the ordered pairs where the curves intersect, but I'm doing x, so I need the x limits, not the y limits. So if I said 1 to 4, those are the y values. So now that I have this, I can clearly say that the area is the integral from negative 1 to 2 of x plus 2 minus x squared dx. Now that doesn't look complicated. So that would be 1/2 x squared plus 2x minus 1/3 x cubed from negative 1 to 2. So I'm going to have 2 plus 4 minus 8/3, then 1/2 minus 2 plus 1/3. Okay, and again, just use the calculator. And my calculator says the answer is 9/2. Okay. Now, is there any type of answer that you would be suspicious of? Anybody?
Maybe a negative value?
Yeah, see, I set up the problem. Nobody told me to evaluate. By the way, an integral can be any real number, positive, negative, 0. But I set up the problem in order to find the area. I set it up so that I have this curve on top, this curve on bottom, so my height would be positive and all that stuff. If this came out negative, I'd be highly suspicious that I completely messed this up, okay? Because I set it up. Negative would be bad. What would another bad answer be? Looking at my picture, I see a physical area. What's another bad answer? What's the next worst thing? Negative would be bad.
Maybe zero.
Zero. Negative probably means I switch the order of integration or I switch the order of subtraction. The negative means I probably have the right idea, but I simply subtracted these backwards, which by the way is an extremely common error, or integrating. So in other words, I can fix that. But if I got zero, that would be really weird because that means everything went wonky because I physically have an area. I can't have zero. So one of the things, if you make an arithmetic error, that's hard to spot sometimes, but if you get an impossible answer, zero or a negative number, when you're setting it up to find a positive area, then that indicates to you, I need to go back and fix it. So again, nothing difficult about this question. Let's try more. All right, this time, find the area of the region bounded by y equals x squared and x equal y squared. This ought to be interesting. So I'm going to draw my picture. So I've got y equal x squared, and I've got x equal y squared. So I'm interested in this little piece right here. Okay. Now, a lot of times when we draw our pictures, we don't do a great job. We make it too big, too small. I can't actually see what's going on. Now, in this case here, I can set this up two different ways. I can set this up with vertical or with horizontal, and both would be exactly the same level of difficulty, because if I set it up with vertical, then I need to solve for y over here. If I set it horizontally, then I need to solve for x over here, but clearly I'm in the first quadrant. Now, can anybody tell me my points of intersection without doing any algebra? When will y equal x squared and x equal y squared at the same time?
0 and 1.
The origin.
Okay, that's one of them.
And 1, 1, 1.
1, 1. Yeah, that was pretty easy, wasn't it? 1 equals 1 squared, 1 equals 1 squared. And by the way, because this is an upwards opening parabola and that's a sidewards opening parabola, there's no points of intersection anywhere else. Well, that made it easy. So let's do this one. Okay, go ahead and mute yourselves again. Let's do this one, horizontal rectangles. Okay, I want to go this way. And again, I always draw the picture because right now, my leftmost, my rightmost. If you have vertical rectangles, you always say top minus bottom. I want a positive height. But when I'm going sideways, which way should I subtract? Left minus right or right minus left? Anybody want to try that one?
That's left minus right.
Well, think about it this way. Why do we go high minus low? Because we say numbers increase as I go up. So if I'm going this way, don't numbers increase from left to right? So then I need to go right minus left in order to get a positive distance. See, this is more positive than this, so I got to subtract right minus left. So right now, this curve is x equal y squared. What's this curve? It's y equal x squared, but it's x equal what?
X equal root y.
X equals root y, and it would be the positive square root because I'm in the first quadrant. Okay, now, by the way, if we had done vertical rectangles, I would have needed to change this to y equals square root of x. So the level of difficulty, the amount of work required for a horizontal versus a vertical rectangle in this problem will be absolutely identical. So now my ith area, I'm going to take the rightmost curve. The rightmost curve is this one. So I'm going to have, how about if I write that as yi to the 1/2? That might make it a little easier. The leftmost curve, that's this one, that would be y squared. delta yi, and the y's are ranging from 0 to 1. Now that I've stated what the area of an arbitrary rectangle, and that's the term we use, it's arbitrary because I could have done any rectangle. Now I can write the integral. We're skipping the entire Riemann sum limit process and going directly to the integral. So 0 to 1, y to the 1/2 minus y squared dy. Now, if I somehow get a negative answer, and by the way, if I had told you to do this on your own, I'd estimate up to half of us would have got a negative answer because it probably the order of subtraction would have been reversed. Because again, it's got to be right minus left, but we may have inadvertently subtracted the other way. So this will be y to the 3/2 times 2/3. This will be 1/3 y to the 3rd power. Okay, so my answer is simply 2/3 minus 1/3, or 1/3. That's it. So a horizontal rectangle doesn't make it a harder problem. In fact, like I said, and I will say this again, every area problem that exists, you can attempt either with vertical or with horizontal. What you're going to find is the vast majority of the time, one of them will present less challenge than the other. In this particular example, it would not have made any difference. It would have been the same level of difficulty, the same amount of work, because the way this is bounded. Okay, that's actually, it's there. So let's try another one. We're kind of getting the hang of these guys. Oh, sorry. Okay, we go. Where's my black pen? By x equal y squared and y equals x minus 2. Okay, x equal y squared and y equal x minus 2. So I wonder what that looks like. Well, we know what x equal y squared looks like now. We just did it. That's y equal x minus 2 would be something like that. Okay. A little more room here. And I want this area right here. All right. So like always, we're saying, I'm comfortable doing vertical rectangles. This is y equals x minus 2. X equal y squared, so this would be y equals root x. What would this be? If that portion of the curve is y equals square root of x, what would this portion be? Anybody?
Y equals negative square root x.
Beautiful. The negative. Oh, because y would be plus or minus square root of x, wouldn't it? Top part would be positive square root. Bottom would be negative because I have to get negative y coordinates. And by the way, that's important because I have a different section here. Now, let's set this problem up. So when I do my vertical rectangle, all right, and we'll call that the ith area. It's going to be top curve minus bottom curve. So, and we'll use x to the 1/2 power. That's easier. So xi to the 1/2 minus xi minus 2. I do need those parentheses there. That was ugly. Minus 2. Delta xi. And then, of course, what is delta x range, or what is x ranging from? Oh, we don't know. We have to find those intersections, don't we? Oh, boy. And by the way, rarely will you be told where things intersect. You've got to be able to find it algebraically. So I need to set these equal or do substitution. Well, let's see. If x equals y squared, then I'm going to rewrite this as y equals y squared minus 2. Okay, I just substituted. So that's y squared minus y minus 2 equals 0. So y minus 2, y plus 1 is 0. So y is 2 or y is negative 1. Well, I'm pretty sure this would be the y equal 2. And I'm pretty sure this would be the y equals negative 1. So now what's x? If y is 2, then x would be 4. If y is 2, then x is 4. Yep, that works. Okay, how about here? If y is negative 1, then it looks like X would be positive 1. Over here, if Y is negative 1, X is positive 1. Yep, that works. See, I always check because I could have made an error. Okay. So going back to here, what is what's my range of values for X? Top curve, bottom curve.
Well, wouldn't one of if we're going to the left, we're not evaluating all the way to the left most of the area of the graph. We're just doing it for the ith rectangle, right?
Why are we not going all the way to the left?
Because then wouldn't that be the origin? Wouldn't that be 0, 0 as the farthest point on the x-axis, right?
Well,
instead of where they intersect, which is 1 away from the origin.
Does that mean that this is 0 to 4? Well, here's the problem. Right now, I have the half parabola on top. I have the line on the bottom. But what happens over here? What happens? Let's say I take that rectangle. I have half parabola on top and half parabola on the bottom. That is a different set of boundaries. Ooh. In fact, right about, hopefully you all see this. To the left of my dotted line, I have one set of boundaries. To the right of my dotted line, I have a different set of boundaries. That means I am going to actually have to use 2 integrals. This is not possible.
Wouldn't an easier way to be taking this one horizontally?
Yeah, but hold that thought, man. Hold that thought. You're ahead of me a little bit here. Okay, but you're right idea. So right now, the top curve minus the bottom curve is only going to go from 1 to 4. So this area here will be the integral from 1 to 4 of, now we'll go ahead and distribute, x to the 1/2 minus x plus 2 dx. Okay, let's go ahead and finish this. And that would be x to the 3/2 times 2/3 minus 1/2 x squared plus 2x from 1 to 4. Okay, 4 to the 3/2. That's square root cubed. That would be 8. So that's 16/3. 16, half of that, plus 8. 1 to the 3/2, that's just 1. So that'd be 2/3 minus 1/2 plus 2. All right. So right now we've got something icky. It looks like 19/6. Now we're not done. That's the area of this portion. We still have to calculate the area of this portion. Oh my gosh, how am I going to do that? Well, let's call that, instead of AI, let's call that one, how about AJ? Because I'm doing something different. And in that case, top curve is the positive square root, but the bottom curve is the negative square root. Ooh. So this should be xi to the 1/2 minus negative, minus negative xi to the 1/2 delta xi. Excuse me. Okay. Now what? Well, what are my x's ranging from here? Now, Nate mentioned before, I'm going from origin to the
0 to 1.
So 0 to 1. Well, that's just 2 times the square root. Agreed? This is just 2 root. So I'm going to say the area is 2x to the 1/2 dx from 0 to 1. Okay, and what will that give us? That'll give us x to the 3/2. Okay, times 2/3 times 2, so that's 4/3. 0 to 1, so that's just 4/3. Boy, so that means my total area is going to be this guy plus this guy. So the answer is 19/6 plus 4/3, so that'd be 8/3, 27/6, that'd be 9/2. Wow, this was a lot of work. Could we have done this easier, Nate? You seem to have a clue on this. Could we have made this easier?
Yeah, since we have make the parabola, the top one, and the line, the bottom one, or just sorry, take the horizontal slice. Or
Take a horizontal slice. Now I'm going to redraw the picture. This is very important that we understand this. Everything we did just now was absolutely correct. But was it absolutely efficient? Okay, don't add my picture sucks. I know. Don't worry about that. This was -1, 1. This was 4, 2. If we take horizontal slices, I want you to notice something. Won't my left curve always be the parabola? And won't my right curve always be the line? Does everyone see that? That means if I do a horizontal slice, I need one integral. That's automatically superior to what we did because what we did required two integrals. And neither one of them were complicated, but it was twice as much work. I would way rather do one integral. And this is a major part of your decision making. So if I do this horizontally, now what I need to read me, I'm going to go ahead and erase this. I don't need this anymore. Okay, so if I go horizontal here, then this is right now already x equals y squared. So this would be x equal y plus 2. Because I'm going horizontal, I have to describe both curves as x equals. When I'm going vertical, I have to describe them as y equals. So now I can say the ith area is, now I'm going left to right, so I'm going to take right curve minus left curve. That's very important. So y plus 2, and now I'm subtracting yi squared, delta yi, and now the y's are ranging from, whoops, I got this backwards. Sorry, I wrote -1. Sorry, that should be 1, -1. Sorry. All right. So the y's are ranging from -1 to 2. Now I can say the area is -1 to 2 of y plus 2 minus y squared dy. Now, before I go any further, you already know what the answer is. Does anybody notice anything about this integral? You guys having a feeling of, I don't know, like deja vu? Anybody? Look at your notes if you're taking notes. Does this seem vaguely familiar to you? Have we done this before? Like today?
Oh, wasn't it the first integral that we took?
The second one. Yeah. Remember the second integral? Not the first one, the second one, I did the parabola and the line, and then you did all that. And yeah, it's the exact same problem. I just turned it sideways. Oh, I'm so mean and devious. I did that for a point. This one, it made sense to do vertical rectangles. I said horizontally, we'd have to do more than one. I took the same problem and I turned it sideways. Now we should go 1, but we should go sideways. This problem, the integral was -1 to 2 of x plus 2 minus x squared dx. The exact same integral. So anytime you find it easier to change direction, vertical to horizontal or horizontal to vertical, you find it easier because you only have one integral versus 2, or rewriting your limits of integration, or your boundaries, I should say, x equal a function of y versus y equal a function of x. This is how you make your decision. I did this problem 2 ways. I did it the long, less efficient way, and it was absolutely correct. And then I did it this way, which was much, much shorter, much simpler. Both were correct. Which one should you choose? Whichever one gets you to the answer faster. That's really how you decide. Okay, so let's try another one. All right, let's find the area of the region bounded by, how about, oops, sorry, no, sorry. Make sure I got this correct. Y equals the inverse sine of x hang on, give me 1 second, making sure I make this not too terrible. Y equals pi over 2 and x equals 0. Okay, I got to make sure it's enclosed. If you ever run into a problem, and by the way, this will happen very occasionally, and probably every calculus book that exists, there will be a bad question. There will be an error. A question will be stated, find the area bounded by, and then you go to draw the picture and it's not bounded at all. It's open. You know, they gave you two curves and it was still open. You go, wait a minute, that's not going to work. Skip it. If you're ever asked, find the area of a region bounded by, and it's not bounded, then the area is infinite. It's basically you're asking for the area of the XY plane. Not a good question. All right, now inverse sine. What the heck does that look like? Well, the other ones are x equals 0. That's the y-axis. Y equals, that would be a horizontal line. Well, I know what the sine wave looks like. Turns out inverse sine just goes the other direction. So inverse sine is going to look like this. So I'm asking for this area right here. Oh, okay, that doesn't seem too bad. All right, so y equals, okay, let's make this easy on ourselves. Well, this is y equals inverse sine x. This is y equals pi over 2. Oops. So when I do my rectangles, my ith area will be top curve, which in this case would be the line, minus bottom curve, delta xi, and x is, oh, darn, I need that point right there. Okay, I know that's something. Inverse sine of what number is pi over 2? Now remember, sine of an angle gives you a ratio, so inverse sine of the ratio gives you the angle. I know that sine of pi over 2 equals 1. So how about inverse sine of 1 equals pi over 2? Ah, okay. So my x's clearly are going to go there. Ah, great, this is a piece of cake. So, and I said, often it's the case that you can just state the integral and you can wave at it and move on. In other words, I'm going to wave at it and move on, and then I'm going to hand it over to Jeremy. Say, oh, Jeremy, you finish it for me. And Jeremy says, oh, no, I'm going to hand it over to Nate. And then Nate says, no, I'm going to give it to William. And do we have everything we said is correct? Is there a small problem from this point on? You know, the derivative of inverse sine is complicated, but how about the antiderivative of inverse sine?
I don't think we have that.
We don't have one. No, we don't have an antiderivative of inverse. Oh, we're kind of, that's a correct statement, but we're dead in the water because we can't integrate that. we know a derivative, not an antiderivative of inverse sine, which means we're done. But wait a minute, I need an answer. I need an answer like now. I mean, the boss is calling, the red phone is ringing, the meteors are headed this way. I don't know what, I need an answer. Well, what do? I can't integrate this with vertical rectangles. Any ideas?
What about horizontal rectangles?
Horizontal. Like I said, I'm mean and devious, or in the words of Gollum, I'm wicked, tricksy, and false, right? No. But if we go horizontal rectangles, that changes everything. Because instead of y equals inverse sine of x, this becomes x equals what?
Sine y?
Sine y. I'm pretty sure sine y is a lot more friendly. Oh, and this is x equals 0. This is x equals sine y. Oh my goodness. Let's call it a j, because we're now doing a different problem. Right curve, which is sine y, minus left curve, which is technically 0, right? Remember, this is x equals sine y, this is x equals 0. I'll go ahead and write the 0 just so we don't lose it. Delta y, sorry, that was a j, not an I. And now what is the range of value for y? Y is going from here to here, so y is going from 0 to pi over 2. So now I can say my area is the integral from 0 to pi over 2 of sine y dy. I don't think that's really scary anymore. In fact, I don't even think that's hard. So this would be the negative of the cosine of y from 0 to pi over 2. Now that negative is huge because what is the, I'll put the negative on the outside. It's cos pi over 2 minus cos 0. What's the cosine of pi over 2?
Zero.
What's the cosine of 0?
1.
If you know that one, you should know that one. The cosine of 0 is 1. So my answer is, oh my gosh, my answer is 1. Yeah. Couldn't do this one. This one was easy. Okay. Point
We
being,
need the negative.
right?
Okay. Yeah.
That, by the way, that's why I said that negative is huge. If I integrate this perfect example, if I integrated this badly and I have a positive there, then my final answer would have been a negative 1. And you'd say, wait a minute, something went wonky there. And again, if you're getting a negative answer, two things. Did I subtract in the wrong order? Do I have my limits backwards? Well, in this case, do I have the wrong antiderivative? A wrong antiderivative will always give you an incorrect answer. There's not that many ways to get a wrong answer. I mean, bad arithmetic is kind of still the number one thing. So this problem right here, it seemed impossible at first. And it turns out it wasn't bad at all. It was actually quite friendly. But we had to turn it. Now, how do I know? Well, really, I can't work with that guy, but I can work with x equals. So sometimes you look at something, I can't go in that direction, but I can go in the other direction. All right, let's try another one. So you see, there is no one problem, but the idea is in every case, if I can describe an arbitrary rectangle, whether it be vertical or horizontal, if I can describe it, and then I can also say, in the direction we're going, there's only going to be one integral because the boundaries are not changing. We had a problem where we had to do 2 integrals because the boundaries changed on us. That's part of the reason you have to draw a picture, because you have to ensure. The mistake a lot of folks make is they just read the problem and they try to write an integral and then it doesn't work and they can't understand why. Well, sometimes it's because they don't see what their boundaries are. So let's try another one. Let's find the area bounded by, let's keep this simple, bounded by y equals 1 over about 10 plus x squared, sorry, comma, x equal, let's do x equal negative. No, I'll just go x equals 0 and x equal x equal 5. I don't want this to be too huge. Oh, you know what? I'm going to change one thing. Sorry. I'm going to put the 10. I'm going to put the 10 on top. Sorry. I want this to be an easier antiderivative. 10 on the bottom. What was I thinking? Now the question is, what the heck does that thing look like? I don't have to have a perfect picture. One of the things I want everyone to realize, your picture does not have to be accurate. It has to be representative. So for example, if the entire graph lives in the first quadrant, then your picture has to be in the first quadrant. You can't be crossing over axes. If I have one curve on top always and one curve on bottom, I don't have to have a perfect picture, but I have to have the correct curve on top. Okay. So I'm bounded by that, oh, and I need one more, sorry. And I need, and y equals 0. I don't have a lower limit yet. Okay. That's important. So now when I draw this thing, I'm bounded by the x-axis. I'm bounded by the y-axis. I'm bounded by the line x equal 5. So now I'm up here somewhere. Now I need this. Well, that's actually not that hard to draw. When x is 0, y is 10. So maybe I'm here. when X is 1, Y is 5. When X is 2, Y is, oh, I see what's happening. As X gets bigger and bigger and bigger, Y is going to get smaller and smaller and smaller. It's never going to come all the way down. So when X is 5, Y is 10 over 26, maybe about here. So what's going to happen is going to look kind of like that. Not really exciting. So I'm finding this area right here. I'm bounded by the axes, by the line, that basically covers that little piece right there, and by whatever this is. If I had continued on the other side, it's kind of a bell-shaped curve. Yeah. So now when I do my rectangle, this is not all that complicated anymore. The area of my ith slice will clearly be this minus 0. So I can just write this. And the range of values for X clearly would be 0 to 5. Okay. Well, this is actually going to be a fairly simple statement. Now, I don't know if I can integrate this yet, but we'll at least set it up. So 0 to 5, 10 over 1 plus x squared dx. If I cannot integrate this, if this presents too much difficulty, then I can consider going horizontal. But in this case, if I chose to go horizontal, does everyone see that I would need 2 integrals because left and right changed? So I really don't want to go horizontal. That's too much work. Do we know the antiderivative of this, anyone? Maybe if I did this, it might be easier. That might make it more obvious. Do we know the antiderivative of this?
Inverse 10.
This tangent.
Inverse 10. Oh my gosh. See, a lot of you are looking at the 10 going, how do I work the 10? And 10 is just a coefficient. So this is 10 inverse tan x from 0 to 5. Now, those numbers automatically, okay, those are ratio values, but when I take the inverse tan of those, I should say, those are radian values. 0 and 5 aren't radians. Inverse tan of 0 and inverse tan of 5 would be radians. So this is 10 inverse tan of 5 minus, now one of them's a gimme. What's the inverse tan of 0? Tangent of what angle is 0?
0.
0. Tangent of what angle is 5 radians? I don't know, inverse tan of 5, whatever that is. That's not a common angle. In fact, if I wanted a decimal answer, I can do this. I'm going to put it in degree mode, first of all. Oops. I'm going to put it in degree mode so you have an idea. If I do inverse tan of 5, it tells me it's about this many degrees. Okay, that's not 30, 45, 60, 90. Nope. It says it's a little over 78 degrees. So now if I put it in radians, which is actually more meaningful, then inverse tan of 5 is about 1.373 radians. Does that number mean anything to me? No, it's a decimal approximation of something evil. So I'm going to say the final answer is 10, inverse tan of 5. That's the answer. If I need a decimal value, I just multiply it on my calculator. That's the exact value, and there is no common angle. Now, if it turned out my answer, was pi over 3, or something like that, yes, absolutely, I would write pi over 3. But that can only happen when I have a common ratio. Okay. So any questions so far? Everybody got this? This is not really all that terrible. I mean, you draw a picture, and then after you draw the picture, you say, okay, what will make my life easier? What arrangement of things? What order of things? And a problem can get dicey. Okay. Now, one of the things we also notice is if I have to set it up in such a way that I need to get a positive answer, then it's really important that we do exactly that. All right, let's do one more of these bad boys. Let's see. Let's do find the region. Okay, find the area of the region bounded by y equal 1 over x, y equals e to the negative x minus 1. And let's see. Minus 1. Make sure I get my picture. Hold on a second. X equal 1 and y, hold on a second, make sure I got that correct. X equal 1 and y equals negative 1. I think that's the last piece I want here. Yes, I think that's what we want. Oh, I'm sorry, not y. I'm sorry, I'm looking at the wrong one. And x equal 1 and x equal, let's say 4. I think that gives, okay, that's what I want. All right, now this one's not going to be all that friendly, but maybe it's easy. I don't know. So let me start big picture here. Okay, there's my y equal 1 over x. And then the last one is e to the negative x. Now, I know that e to the x goes this way, so e to the negative x goes this way. When x is 0, I have e to the 0, which is 1, but then this is minus 1. So this actually is going to go like this. So I can just kind of this. These aren't exactly the same. This is just a lousy drawing. This is on top, this is on bottom, and I'm going from here to here. Remember I said representative, doesn't have to be perfect. Technically I should make this cleaner. There actually is a horizontal asymptote, by the way. There's a horizontal asymptote. I should probably make that a little cleaner. How do I know? Because y equal e to the negative x has the x-axis as a horizontal asymptote. I just dropped it 1. So the line y equal negative 1 is a horizontal asymptote. Now this looks absolutely scary until I realized that, oh, if I just draw a vertical, that's not too bad. I don't want to go horizontal, too much work. And then I have to rewrite things, too complicated. Too scared. Okay, so this is y equals 1 over x. This is y, this one here is y equal e to the negative x minus 1. So the area of my ith slice is this minus this. And the x values clearly are going to range from 1 to 4. That definitely makes it not the worst thing I've ever done. I mean, this is not fun, but this is also not terrible. Now I can say the area is the integral from 1 to 4 of 1 over x minus e to the negative x plus 1 dx. And looking at that, none of those terms are difficult to integrate, are they? Those are all pretty easy. Okay, what's the antiderivative of 1 over x? Anybody?
Log x.
Yeah, log of, careful now, absolute value.
Absolute value of x.
We had a problem on the quiz that was log of absolute value of x, and you had negative limits, which threw a lot of people at first until they realized, oh, the negative limits don't matter because I'm taking their absolute value. So I write this. Now, when I evaluate these positive limits, life is going to be good, but I still write the antiderivative now, this guy. The antiderivative of e to the negative x is e to the negative x, correct?
Negative e to the negative x.
So is this plus or minus?
Positive, because there's a negative inside.
Good, because when I differentiate, my chain rule factor is a -1. So that means that's a plus, because when I differentiate, I'm going to multiply by -1. By the way, this is how I check. The derivative of this, okay, the derivative of this, okay, and then this is just x. The biggest mistake we're going to make is probably right here, right? A plus or minus error. We don't want any errors. Don't like errors. Not a big fan. Okay, so this is log 4. I don't need to say absolute value for it. It's just 4 plus e to the -4 plus 4 log 1 plus e to the -1 plus 1. Now there's one gimme. What's the one gimme?
Log 1.
And that's 0. That's gone. Now, technically, we should write these as 1/, but we should write them as 1/, but it really doesn't matter. When people say you can't have a negative exponent in a final answer, that typically is when you have variables to negative powers. If you wanted to say e to the -1st power, that's a number. So writing that as either -1 and 1/e, it's not really that, it's not a big deal. But if I said my final answer was x to the -1, no, we typically will write that as 1/, because we call that a simplified answer because it's function. If you want to write 1/, that's fine. I have 4 minus 1. So this is log 4. 4 minus 1, I'm just going to hit say plus 3. Now, if you want to do this, this is fine. And that's my final answer. Okay, it's ugly, but it's correct. If I needed a decimal, I would calculate it. I don't need a decimal. Always give the exact answer. And then again, if the situation dictates that you need a negative value, and you say, but in math, we never do. Well, but be mindful, I might be asking for something that has units. So for example, next semester, you're going to do things like calculate mass, calculate work, calculate force. So if this answer represented something with units, then I probably do want to give a decimal value at the end of this, because I'm actually saying it's this many, pounds or, whatever. But right now, this is a unitless answer. Technically, this represents an area, but my area doesn't have units. Okay. Now I don't care, but a lot of people, well, okay, in physics, this is an absolute. I gave you a unitless question. This is an area problem. What are area units typically? What do they typically look like?
Red.
Yeah, something squared. Yeah, I like it. Just something squared. See, length units would be whatever units, and the area would be the square of that unit, the volume would be the cube of that unit, and so on. If this was a physics class, believe it or not, I could remember when my daughter took physics 195, and she'll never forget this. And this is mean and devious, but this is what they do. She took physics 195. First quiz, that was so gnarly. She worked so hard and she finally got everything. And everything was a unitless question. It was integrate. It was basically calculus stuff, but there were no units given on any question. And in fact, it wasn't even areas and volumes. It was just do this calculation. She got a 0 on the quiz because the instructor wanted after each calculation the word units. Even though there were no units given, there was no area, volume, or length, so you didn't know what to do with those units. Could have been work, it could have been force, it could have been mass. The instructor wanted the word units, didn't tell anybody that. So my daughter got a 0. The only people that didn't get 0s in the class, I think it's the funniest part, and I know the instructor. Do you know who the only people that didn't get 0s in the class? Anybody want to guess?
People who retook it.
The people who were retake it, the people who had failed it the previous semester, and they were not about to share that knowledge. And my daughter wasn't pleased, and I joked with the instructor. I said, "You do realize you're 100% wrong." With what do you mean? I said, "You can't use the same symbol for units for different things. You're using the same symbol for length, area, volume, mass, force, work, power." I said, "You can't." So in other words, if you don't indicate you're finding area versus volume, then writing the word unit for each answer is absolutely incorrect in every conceivable. And they said, "Well, it doesn't matter. I just wanted to teach them they have to give units to every answer." It's it'd be like saying, how many French fries do you want? And you said 5. Nope, you're wrong. You had to say 5 French fries. That's kind of the reason. Yeah, I personally, I found that punitive and really silly to penalize people for not putting in something that doesn't make any sense in the answer when no units are given. We work with unitless problems, period. Next semester, the first 2 weeks of the semester, we work with units. And then we don't really again until maybe the end of Calc 3. So in the math, we're interested in how to calculate the answer. But I always want you guys to be mindful if units are involved, then it really is important in the final run. We don't have any units, so I don't need you to write units squared. It wouldn't be incorrect. And it's not even a bad idea because it gets you used to it for another class. I just don't need you to do it in this class. All right. So